Lastly, but actually importantly, since it turns out that many inorganic materials have cubic lattices, we will come to the cubic lattice, and I think I've implied this before in previous lectures, that the restriction on z has been 0 so far. We just say that T3 is going to be in normal direction, and the only thing we have required is that it appears on top of other symmetry elements, so that, for example, a threefold axis has to fall on top of another threefold axis as I translate upwards, because the axes carry through three-dimensional space. So, however, we can now say, all right, that's fine, but instead of letting the cell in the, let's say, the C direction be arbitrarily large, let's make it identical so that A1 equals A2 equals A3, and that's what we're going to do. So where we had before always T3 being 0, 0, and just putting Z, we're actually going to make this equal A, where the cubic system has all 3 dimensions equal to A. So if it's cubic, we already know what kinds of systems we're dealing with. Think 4, 3, 2. Right? We had a fourfold axis, threefold axis, twofold axis. And there's many different ways to come in here. You could start with the point groups 2, 3 and 4, 3, 2 and eventually get here. But the truth is, if it's cubic, we know that these symmetries are there. And so now all we have to think about is what happens when we think about various translations and think about in the table later what kind of point groups would be compatible with that. And we kind of know that too from our three-dimensional point groups. With a fourfold axis here, we already know the story with that. If you were to look at this representative cube, and this time it's not representative cube, it's actually the unit cell, have simply the z translation equal to A3 right above the opposite corner. And of course, this is simple cubic. You can also imagine in a cubic structure, since the corner of P4, the center, have same symmetry, you definitely have an option for going up, taking this fourfold axis, going up, stopping. So really this is actually the same as tetragonal, it's just that we've restricted the exact height here to A, which is the same as here and here. And so it's just a really kind of a specific case of tetragonal, and then we could do our 2t, come back here, and all of a sudden we would have the body centered option. Now, you can't see from this how you get face center because remember how we talked about you have a twofold, and if you kind of go up here and try to go on the face, it doesn't work because you'd have this remember this fourfold axis is coming through here, and you try to put it on the face going through here, and of course there's a we don't have a fourfold axis here, right? So that causes a problem. Actually, we have an axis coming out of here which is twofold, but definitely what we don't have is a fourfold that's shooting straight up through the edge. So it would appear that we can't get a face centered. However, of course, we know that there is a face centered. That's one thing that bothers us. But the second thing is to notice that if we build a simple cubic base, and this is going to be the same trick that we had to make the equivalence, and well, not the same trick, but similar trick. But here we're going to redefine the base lattice. So up till now, we've been looking at it as this being the lattice of choice. But what we could do is choose a centered base. And of course, as you know from the other thing, we do that. The minute that you decide to take a centered base, now you've kind of forced, first of all, sort of a face-centered thing because you made the base that way. And the question is, will this, work in the new, right? And of course it will, because all you've done is reposition this. And now if I make this the fourfold axis in the middle, this over here, this will show up on all sides. And so now I produce a face-centered cubic lattice. So what it looked like was I had 13 lattices up to the bodied centered cubic, but with the redefinition of base, the one that wasn't so obvious, I ended up with a face-centered cubic, and that added the 14th Brave lattice. And so we have, one from triclinic. From monoclinic, we had two choices because the side and the bodied center were the same. Ortho, we had 4 because we discovered the face-centered. Tetragonal started to reduce the number of choices again because we only had 2, the primitive and bodied center. And then hexagonal, we had primitive. And then we had the rhombohedral. And then with the cubic, we ended up where we had the primitive and the bodied center, and then finally the more elusive one, the face center. And so we had 3. So when you add that up, it's 3, 7, and 14. And there you have it. So we'll actually summarize in a table next time, because what I want to do then is show you that we kind of use the point groups, or some of the point groups in 2D to generate these lattices. But now we'll go back and look at our 3-dimensional point groups. And with that knowledge, we'll make a table where we can show what point groups are compatible with it. And then you can see how they would come together, even though we're not going to do out all of the 230 available crystallographic 3D space groups.